So in today's lecture, we are going to continue with the framework of semi-definite programming. I'm going to see one more really cool application of this framework. So last time, if you recall, what we had seen was an introduction to this whole idea of expressing a combinatorial optimization problem as an integer program, but not as a linear integer program, but as quadratic integer programs. That is, the objectives and the constraints were quadratic functions of the variables involved. Okay. And after this, what we did was relax it by not just allowing these to be continuous variables, but actually we relaxed them to being vectors. And these vectors were in some high dimensional space. So what you had was, for every single variable, you would have a vector lying in some n dimensional space in the relaxed version of the problem. Now this was called a vector program, which is just another name for what is a semi-definite program, and we justified why this name semi-definite programming was used and how it comes up. And it kind of argued informally that this can be solved to some epsilon accuracy in polynomial time. Okay. Now, and as an application of this, we had seen um, the max cut problem, where we did the relaxation using not 0, 1 variables as was customary in most of the linear programming parts that you have seen, uh, but we used -1, +1 variables. Okay. And the reason for this was it gave us a nice geometric view of the solution to the relaxed SDP as lying in some n-dimensional space, with the vectors corresponding to the variables being points on an n-dimensional sphere, right? And the way we round this solution was to choose a random hyperplane, okay, which cut the sphere into two halves. The vectors on one side corresponded to vertices being on one side of the cut, and the other side was the complement of the cut. Okay. And it turns out that this gives the best known ratio. Now, one small point that I did not mention was that the algorithm can actually be de-randomized, yeah, although it's not important for our purposes currently. Now, in today's class, what we're going to see is the following. I'm just going to recap this idea of relaxing, that is formulating a combinatorial optimization problem as a quadratic form and relaxing it into a SDP. So we're going to see an example using max2sat. The rounding part of it is going to be part of your problem set. Okay. The main application for today is how to color three colorable graphs. Okay. And I'll both define this problem, and we'll see a really nice algorithm for it. So let's look at the first problem I had mentioned, that of max2sat. Now, given the definition of max-sat that we have seen a few lectures back, it must be clear what max2sat means. In the input, uh, you have a Boolean formula, uh, which is basically a disjunction of, which is a conjunction of some clauses. So we have m clauses. There are n variables that are involved in this, either as themselves or as their negation. And therefore you have you have exactly two literals per clause. And what you want to output is an assignment that satisfies the maximum number of clauses. Now, unlike the tree-sat version, actually just the decision version of this, that is finding an assignment, or rather, let me put it as deciding just whether P is satisfiable or not. So this particular problem is in polynomial time. Okay. However, finding an assignment that maximizes the number of clauses that that are satisfied in phi, this is NP hard. Okay, and that's a problem that we want to write an Sdp formulation for. So the first thing to do is to write out, as you had seen for max cut, a quadratic formulation of the problem. Okay, that is using variables which are integer, a quadratic integer program for this. So for this, I will introduce variables yi, which actually take ideally the assignment that the variable xi takes in the clause. Okay. So in terms of the variables yi, we want to express the fact that a clause is satisfied. So suppose the clause Cj looks like xi, or let me write, looks like x1 or x2. How do I represent Cj as an arithmetic formula that is 1 if the yi's are satisfied, if yi or if y1 or y2 is 1, and is 0 if both are 0. So clearly, suppose I define that polynomial that I want for Cj as v of Cj as the following. Now this polynomial, which I call v of Cj, is 1 if either of y1 or y2 are 1, and it's 0 if both are 0. Now this is great. So this is indeed a quadratic polynomial. So let me just expand this out. You can write out similar polynomials for if the CJs are, say, something like x1 or x2 bar, or x1 bar or x2. So writing it out gives us 1 minus an expansion of the product term that was there, and this simplifies to just y1 plus y2 minus y1 y2. Now ideally what would I have liked? Like in the max cut, for some reason it will be nicer to express the quadratic objective in terms of variables that are -1 or 1 instead of 0 or 1. Now this is not a big deal because we can just make the transformation. Suppose I call the variables zi as 1 minus 2 yi, then we know that zi is 1 if and only if yi is 0, and zi is -1 if and only if yi is equal to 1. Okay, so expressing the value of the clause Cj in terms of zi and in terms of z1 and z2, we get okay, and simplifying this expression gives us 3/4 minus z1 by 4 minus z2 by 4 minus z1 z2 by 4. So we can verify this. Now great, so we do have a quadratic polynomial which denotes the value of Cj. So the problem here is that unlike max cut, we also have some purely linear terms. Okay. Now recall that in the max cut, we could have relaxed it into a vector form by replacing the pairwise products of the variables by corresponding inner products of vectors. But then what do we do to terms like just purely z1 or just z2 which occur in this expression? Well, the trick is to actually introduce a new variable z0. Okay, and z0 you can think of it as always being just 1. And you can write this product or this polynomial as the following. Okay. Now with this new variable z0 added in, this is actually every term of degree either 0 or 2. Okay, and therefore now we can relax it. Now you can do a similar operation for clauses of other forms. So either say x1 or x2 bar, or bar or x2, or x1 bar or x2 bar. So for each of these cases you get a polynomial in degree 2 in which the terms are either degree 0, that is either constants like 3/4, or they are quadratic terms. Okay, so degree 2 terms. If we move on to the SDP relaxation, the objective will involve the sum over these clauses of the value of the clause, and we'll replace all of these quadratic terms by inner products. So introduce one vector vi for each zi, where vi, notice that because there are n+1 variables, the vectors lie in some n+1 dimensional space. And if you look at the clause that you have considered, the corresponding term in the objective gives a term of the form 3/4 minus inner product v0 transpose v1 minus v0 transpose v2 minus v1 transpose v2 in all by 4. Okay, so now you can similarly express other clauses. Let me call this particular vector form as v bar of cj. So for phi, the objective looks like you want to maximize summation j is equal to 1 to m v bar of cj, such that now all the vectors are supposed to be plus or minus 1. So you should just have for all I, this includes the v0 vector all the way up to n. So this is the SDP relaxation for a given max to sat formula. So just a small point about the role of the vector v0 in all this. V0 is kind of denoting the fixed vector which denotes the zero assignment to a variable. So this is all in n+1 dimensional space. Now if a vector for a variable I is close to v0, then you would expect that the SDP is telling that you should kind of assign this variable I also a value of 0 in the final assignment. And if something is aligned far away, a Vj is at a large dot product with v0, then it says that you should possibly assign Vj the value 1. Now you can use hyperplane rounding to again get a 0.878 approximation for this. And using this you can get a slightly better approximation for the general maxsat problem where you don't have a limit on the number of clauses. a limit on the size of each clause. Okay. So now that being said, I will leave the details to the next problem set. Let us move on to the problem of the day, which is coloring three colorable graphs. Now, most of you must be already familiar with the problem of graph coloring in general, which states the following. You're given an input graph P, I, and you want to assign colors to the vertices. So I'll call the colorings by chi, which is a function from the vertex set to some fixed integer k, such that for all edges in the graph, you want chi of I not equal to chi of j. That is, no edge is monochromatic. Now, of course, we want as small a value of k as possible. And because basically we want to color the vertices of the graph using the minimum number of colors. The chromatic number of the graph, denoted by chi of g, is the minimum value of k for which g has a valid coloring. So now, turns out that coloring is a really hard problem. And we'll get some idea of how hard it is when we see the algorithm. But it's actually hard just for all values of k greater than equal to 3. What do I mean by this? If a graph is two colorable, then you can find a two coloring. And this is just the problem of whether the graph is bipartite or not. And another easy case to think about is the following. If G has maximum degree delta, then there always exists a delta plus 1 coloring for it. Yeah, I will leave this as an exercise. It is just a simple greedy argument to show this. You can actually find this delta plus 1 coloring very easily. Now, those were kind of the easy results. The hardness sets in if you want to decide whether chi of g is equal to even 3 or not. This decision problem is NP hard, and hence you can kind of guess that approximating the chromatic number of a graph is also NP hard. In fact, it's really NP hard, and so we are looking at, so to say, more tractable problems in some sense and trying to simplify our question. And the way to do that is the following, is to look at challenge questions. Okay, and a challenge question takes the following form. Okay, a person comes along and gives you a graph that he promises is three colorable. Okay, so given that the graph is three colorable, okay, so there's no longer a decision version whether chi of g is 3 or not. It is given that it is 3. Find the coloring. And in fact, we are not even asking you to find a 3 coloring of the graph, but we are saying just find a coloring with as few colors as possible. And this looks like a drastic simplification of the original problem of approximating the chromatic number of the graph. Uh, However, it turns out even this problem is notoriously hard. So assuming P not equal to NP, we cannot even find a 4 coloring of the graph in polynomial time. And assuming the unique games conjecture, in fact, a modified version of the unique games conjecture, uh, we can't find a million coloring of the graph. That is, you cannot color the graph using even a million colors. Well, actually, the statement says any constant number of colors in polynomial time. And this is really surprising, but that's just how hard the problem is. And the problem that we'll consider for today's lecture is precisely this. Given a graph is tricolorable, we want to find a coloring of the vertices of the graph that is valid using as few colors as possible. So the problem for the day, as input, has a three colorable graph. The output that we want is a k coloring of the graph, and the objective is to minimize k. Now what we'll see today eventually is a algorithm that will color the graph using something like n raised to 0.25 log n colors. Okay. Now this seems ridiculous because the graph is just three colorable, and the best we are going or we are able to do is to output a coloring with n raised to 0.25 colors approximately. That's a huge gap. Uh, Actually, we are not very far from the best known for this problem. The best known algorithm, which was around 2012, building on a large series of works, including this particular SDP based relaxation and rounding approach, was a 0.038 log n approximation. We won't see this in today's lecture, and it's actually out of the scope of this course, but it puts into perspective that we are not too far from the best known. It also turns out that actually proving hardness results for coloring is notoriously difficult. Okay, so you can prove better hardness results for hypergraph coloring uh, However, for coloring, uh, as we'll see possibly in a few lectures, proving hardness results for graph coloring problems are particularly not amenable to the kind of results that the PCP theorem gives us. Okay. That being said, let's go on to the problem that we want to solve right now. So let's start by giving a square root and coloring of the graph. Now this is due to Wigderson. It's often sometimes called as Wigderson's trick. The idea is the following. Let us look at our graph. Now we know that we can find a good coloring of the graph if its maximum degree is low. So while the graph has a vertex of degree greater than or equal to square root n, let me call this vertex I. So you remove I, color it with a color. So you're using one color for I and look at the neighborhood of I. If you look at the neighborhood of I, which I'll denote by gamma of I, this is a set of vertices, and if you look at the subgraph on this set of vertices, it is going to be bipartite. And because this is bipartite, we know from our previous observation that you can actually two color a graph given that it is bipartite in polynomial time. And at the end of this, what you do is you have removed I and its neighborhood from the graph. Because they are already colored. And you repeat this process on the rest of the graph until the graph has no vertices of degree greater than or equal to square root n. Now the point is every time I repeat, we use new colors. Now in every loop, notice that we have used up three colors, right? One for I and two for its neighborhood. And every time we use three new colors, so if this loop runs for k times, then at the end of this loop, we have used up around 3k colors for coloring a subset of the vertices. And this, at least partially until now, is a valid coloring. So the remaining graph has got maximum degree square root n, right? And so you can find a greedy coloring with, or rather maximum degree is square root n minus 1, so you can find the greedy coloring with square root n colors. So use square root n completely new colors and color the rest of the graph. So at the end of this process, how many colors have I used up? Well, how many times can the initial iteration run? Okay, the loop run. Well, notice that at every point or every iteration of the loop, I'm reducing the number of vertices in the graph by square root n, and there are at most n vertices in the graph. Okay. So the number of iterations of the loop is at most square root n. In each iteration, I'm using 3 colors. So the loop execution uses 3 times square root n colors. And after the loop, we use square root n colors. It implies overall we are using 4 times square root n, which is order of square root n colors. So we are able to 3 color the graph using square root n colors, 4 times square root n colors. Now we chose the parameter of the degree to be square root n because it balanced out the two parts of the number of colors used within the iterations versus what is used once the iterations are done. This can be generalized in some way, and that generalization will be useful. So if I use a threshold delta for the degree, then the iteration runs for n over delta. Okay, and then you use delta plus 1 colorings for what is left over, delta plus 1 colors for what is left over at the end. So with threshold delta, instead of square root n, you use something like order n over delta for the loop plus something like delta plus 1 for the remaining part of the graph, and we balance this delta out to be square root n to match these two up. Now this was a purely combinatorial algorithm, and it turns out that combinatorial algorithms can get you up to at most n raised to 0.375 log n, which is the best known due to Blum. And to go beyond this, the only known algorithms use semi-definite programming. So we'll write the SDP relaxation for the problem, not with the idea of minimizing the number of colors required to color the graph, rather using the fact that we want to actually find an exact 3 coloring of the graph. Okay, so the actual writing of the SDP will be slightly different from what you have seen before. That is, we won't start with a quadratic form and then try to relax that into a vector form. Rather, we're going to directly go into a vector form. So let us look at the following. What would be a valid arrangement of the vectors corresponding to a 3 coloring? If I had a vector for every vertex, I could have used the following in 2 dimensions. Okay. That is, I want to color it using 3 colors. So all the reds, for instance, go here, all the blues go here, and the greens are here. Okay. So given a vector for every vertex, we would like the arrangement of the vectors that puts the same colors as collinear and different colors or distinct colors at, so what is this angle over here? Just looking at it in 2 dimensions, this angle is 120 degrees or 2 pi by 3, right? Okay, so the vectors of one color all align up, okay, and for different colors they are at 120 degrees from each other. That is, we want a feasible solution to the following problem. Well, there is no objective, we just want a feasible solution such that for all edges, okay, so for every edge the two endpoints have a different color, so we should have the corresponding vectors, the inner product, well, they all lie on the unit circle and the angle is 2 pi by 3, so the inner product is minus half. So this is coming from the fact that want one times cos 2 pi by 3 minus half. And of course we would like the vectors to all lie on the unit sphere. So for all vertices the corresponding vectors are unit vectors. So clearly the above has a feasible solution if G is 3 colorable. Okay. And the feasible solution in 2 dimensions is the one that is pictured above. But of course the vectors that we have in an SDP, as I said before, the dimension is up to n dimensional, right? And we don't have a control over that. So if the solution were 2 dimensional, then we could just read off the coloring. Okay. But now the vectors is allowed to be n dimensional. So using the n dimensional vectors, can we get a good coloring of the graph? So an assignment of vectors that satisfies the above program is often called a vector coloring, or rather a vector 3 coloring of the graph. So let's go ahead and see how does one actually use these n-dimensional vectors to extract out a coloring for the graph. Now the idea is very similar to what we had seen for MaxCut, that the SDP in some way does indicate what are the colors. Right? So notice that we had set up the SDP in a way that the edges in the graph have vectors which are aligned far apart, that is at 2 pi by 3 from each other. And therefore, if vectors are close together, then it seems to indicate that they should not be edges. Okay, and vice versa if the vectors are far apart. Now, the starting point of the rounding algorithm is going to be the following simple observation. Okay. That is, a three colorable graph has three large independent sets of size n over 3 each. Okay, that is because every coloring by itself, uh, every color by itself constitutes a set of vertices that have no edges between them, and so it must be an independent set. So the algorithm is actually going to proceed by finding large independent sets. Okay, and the algorithm that we will see might at a very superficial level remind you of the LP randomized rounding algorithm that we had seen for independent set. So let us say we find an independent set of size gamma times n. So now the whole independent set can be colored using a single color. Now what remains is we keep these vertices aside and we have 1 minus gamma n vertices, right? And on the subgraph consisting of this 1 minus gamma n vertices, we repeat the above procedure and using a single color at every step, a new color at every step. In each of these steps, we are going to use the fact that the graph that we have at every point is three colorable. So what happens after k iterations? The number of vertices left looks like 1 minus gamma raised to k times n, because we have only a 1 minus gamma fraction of remaining at every iteration. So in approximately 1 over gamma times log n iterations, we have only one vertex left. Okay, and why is that? That's because 1 minus gamma raised to k times n is equal to or is less than equal to exponential minus gamma k times n, and for this to be equal to 1, this implies that k looks like 1 over gamma ln n. Okay, so in so many iterations you get down to one vertex, color the single remaining vertex again with a new color, and therefore we have a coloring of the entire graph at the end of this process. Okay, so the number of colors used is equal to 1 over gamma natural log of n. Okay, something of this order. So now what we have done in this procedure is reduce the problem of coloring the graph to finding large independent sets in the graph. Okay, because the larger the independent set that you find, that is the larger the fraction gamma is, the smaller the number of colors used is. Okay. And of course, we had seen that we cannot find a very good approximation to the independent set in general, but here we can do a good approximation because the graph is three colorable. So I hope the overview of what we're going to do is clear. So let's go on to finding this large independent set next. Now what we are going to do is, because we are dealing with randomized algorithms, as expected, we are not going to find an independent set of exact size gamma n at every step, but rather we'll find an independent set of expected size gamma n. Okay, and this is in a 3-colorable graph having n vertices. Now, using the kind of tools that I had shown you for probability, that is Markov's inequality followed by amplification, you can say that with high probability, that is with probability something like 1 minus 1 over n raised to c, for as large a constant c that you want, you can change the algorithm to, in polynomial time, can get an independent set of size gamma n over 2. Okay, so you'll just be off by a factor half with high probability from your expected size. And of course, this itself, as you can argue, is going to be enough. To get the same kind of coloring, because all we have is gamma replaced by gamma over 2. So here's the goal that we're aiming for finally. So given a 3-colorable graph, we want to find an independent set of expected size gamma times n, where n is the number of vertices. Okay. Now the gamma that we'll manage to get is something like 1 over delta raised to 1/3, or 1 over cube root delta, where delta is the max degree in the graph. Now this does not look anything immediately like the n raised to 0.25 coloring that I had promised you earlier, but we'll come to that at the end of this. Let us keep this as the intermediate goal, and the way we do find this large independent set is to use the vector coloring. So recall the vector program. There was no objective because all we were looking for was a feasible solution. So for all edges, the inner product between Vi and Vj was equal to minus half. And of course, we had that the vectors lie on the unit circle, okay, or the unit sphere in n dimension. Now, as I said before, the intuition behind this SDP's rounding is going to be the fact that if the vectors are close together, then most likely you don't have edges between them because edges are spread at 120 degrees apart. So what we are going to do is, actually, if you have a vector of this form, we are going to take a cut, okay, at some threshold in the sphere. Now I'm going to define how we are going to do these cuts in a moment, such that the inner product with this vector is at least some epsilon. So we're going to define the spherical cap. We're going to choose a random vector, a spherical cap around the vector. And for every vector from our solution of the SDP that lies in the spherical cap, we try to get a large independent set. So notice the difference from our hyperplane rounding algo, which was discussed for max cut, in which we chose a random vector on the sphere, right? And we use the hyperplane corresponding to that normal vector to split into two parts. Okay? And actually, it's not very different, that except here when I say a spherical cap, if you're a little careful and are attentive, you can kind of argue. So here's my random vector R. Okay? So the vectors in this cap satisfy that the inner product between the vector and my random vector R is at least some threshold T. Okay. Now, in the case of max cut, all we needed was the sign. Here we are going to actually keep an explicit threshold. Okay. Secondly, the vector R that we choose randomly to take an inner product with is not going to be just a vector on the sphere, but it's going to be a random Gaussian vector. And we will need properties of the Gaussian distribution in n dimensions. So I'm going to spend the next 5 minutes or so reminding you, or if you don't know, just recalling the properties that such Gaussian vectors satisfy. Now, to start off with, we'll just consider the one-dimensional Gaussian distribution. And the given parameters that we'll be seeing, it's called the standard Gaussian. So this is a continuous distribution. And the points in the distribution, that is, the distribution is over points in the real line. So the density function for such a distribution is basically this exponential, okay, where the exponential drops on with the square. This is parameterized. This actually standard Gaussian is called n of 0, 1, or the standard normal distribution. The way the density function looks is something like this. 0 is the mean. Okay. And if you substitute 0 here, you see that it comes something to 1 over square root 2 pi, the top, and then it decreases exponentially on both sides of the mean. Okay. So it drops down to 0 really fast. Okay. The 1 here is the standard deviation. And the way you think about the standard deviation for continuous variables is basically this is kind of the limit in which a constant mass of the probability lies. So the probability that you have things outside the standard deviation, so this is 1 minus 1. So this probability is some constant. And if you're not familiar very much with the definition of these density functions for continuous variables, a curve like this, which gives you the density function, basically says that the probability that a random variable x, which follows the standard Gaussian distribution, lies in say x and x plus dx is p of x times dx. If you take a very small interval over here around x and you look at the corresponding phi of x, the probability that your random variable lies in this small strip on the x-axis is given by the area under the curve between x and x plus dx. Now, it's often useful to define a quantity which is known as, which we'll call as n of t, which is the probability that a random variable x, which follows this standard Gaussian distribution, is greater than equal to t. Okay, and this is by definition equal to the integral from t to infinity p of x dx. So it's just the probability that a random variable following the standard Gaussian lies anywhere to the right of a threshold t. Now n of t follows some properties, although we cannot compute n of t explicitly for every t, because actually integrating this is not that easy. We can surely find bounds on n of t, and that is what we'll use. It's in fact okay. So n of t is at most 1 over t times p of t. Oh, I used, and it is at most at least 1 over t minus 1 over t cubed times p of t. Okay. And this is going to be quite an important property that we'll use in a key way. I'm not going to prove this. You can prove it using some standard bounds on what phi of t is, because phi itself is not easily integrable. An upper bound on phi and a lower bound on phi you can consider as some functions which are integrable, and prove these bounds. But it's more of an exercise rather than useful for us in today's context. Just to remind you, phi of t looks like exponential minus t squared by 2. Okay, it's 1 over square root 2 pi exponential minus t squared by 2, which is what you put both on the left hand side and the right hand side. So let's go on to the n-dimensional standard Gaussian. Okay, which is basically a vector in n-dimensional space where every coordinate, suppose I take r is equal to r1, r2, so on until rn. Okay. Each of the ri's is independent and identically distributed to the others, and they are all standard Gaussian variables. Okay. So every coordinate is independent and identically distributed according to the distribution that we had seen above. So the first point about this, and possibly one of the most important points, is that this distribution is spherically symmetric. And you can see this already by noting that no single coordinate is all that important. Okay, that is, no single coordinate stands out. They are all um, treated the exact same. So you have the distribution of the n variables taken together is just the product is the density function of x, okay, where x is now in Rn and you have x1 to xn. Now if you look at this is nothing but the 2 norm of x, because once you multiply out all the coordinates in the exponentials, the xi squares add up to give you norm of x squared. So what does this mean? This means that for any x, so let us take, just for illustration, a two-dimensional Gaussian, and what does it look like? Well, you would choose the x1 coordinate to be according to the standard Gaussian on x, right, on x1, and it would turn out to be some x1 over here. Let me write this as x1 and x2. Similarly, x2 you would choose independently to be a standard Gaussian along the y-axis, along the x2 axis, and get a point here, and the combined point that you have chosen according to the standard Gaussian distribution in 2 dimensions would be this. Okay. Now what the spherical symmetry tells you is that all points in the same radius around the origin, which is the mean, has the same probability. Okay. Now that is a little loose to say in the term of continuous variables, but what I mean to say is that the density function is invariant along a circle. Okay, so what the density function looks like is that it is densest in the center. So let me draw it over here. It's densest in the center and kinds of drops on exponentially, if you see, in the norm of x around. Okay, so this is what the density function looks like. Okay, so think of it as being a hill. So if I had to draw this in 3 dimension, it would go something like this, with the density function dropping down close to 0 according to the norm of x. Now a second crucial property is the following. If you take an n-dimensional Gaussian, standard Gaussian, and you project it on any coordinate or any vector, then the resulting thing is the corresponding standard dimensional Gaussian in that subspace. So if R is an n-dim Gaussian, U is a unit vector, then the inner product between R and U, notice, is a random point along the direction of U. Okay, and just viewed along this direction of U, it is going to be a one-dimensional Gaussian. So for instance, in the two-dimensional Gaussian case, if you take a line U, okay, and you look at the distribution along this vector U, this is going to be a one-dimensional Gaussian. Okay, and this is a really important property that we'll use. The same holds for any subspace. If you take a two-dimensional subspace and project down an n-dimensional Gaussian into that subspace, that will also be a two-dimensional Gaussian. So using these tools, here's the rounding algorithm that we'll analyze. So this was a vector program which was guaranteed to have a feasible solution because G was 3 colorable. So you solve above to find some feasible solution. And notice that it might not look exactly like the ideal picture drawn above because the vectors lie in n dimensions and not in just 2 dimensions. Now you pick a standard n-dim Gaussian vector, which I'll call R, and we find the set I0 is I such that R transpose the inner product with Vi is greater than equal to T. Okay, so we'll set T greater. So it's some threshold and we want the inner product to be larger than that threshold. Then we'll call the set I0. And within I0, we look at which points have got no neighbors. So this is the pruning step, which is similar to the randomized rounding using the LP. We did a similar thing. We first found a candidate big set and we pruned it down. And the goal is to analyze. So clearly I1 is an independent set. And that is the one that will output. So to analyze the expected value of the size of I1, we are going to look again like before the expected size of I0 minus how many we have removed. So what is the size of the set I0? Okay, now I'm going to call so this is supposed to be I1. Now by linearity of expectation, this is summation I is equal to 1 to n of just the probability that a single vertex I is included in the set, right? So this is the probability that the inner product with my random vector R is greater than equal to the threshold T. And then of course you have what you remove, which we'll come to in a moment. Now notice that by property of our standard Gaussian vectors, this is a one-dimensional Gaussian. And the probability that a one-dimensional Gaussian is greater than T is equal to, we had defined it as n of T. And we are of course subtracting out what was removed out. Okay. Now let us try to get this term. Now how do we bound this term? Well, you had an initial candidate set I0 and you removed out all vertices that had an edge to another vertex in I0. So if you had both I and j, you would remove both I and j. Okay, so this is not an iterative process in which you remove a vertex and then the other one is not there. You remove both because both of them have an edge within I0. Now I claim that this quantity is, again, we are going to keep using linearity of expectation, is equal to the summation of I equal to 1 to n, the probability that I is in I0 and there exists ij which is an edge such that j is in I0. Right? And now for this I can use the union bound to say that it is the sum over edges, that is the neighbors of I basically, so this is the neighbor set, the probability that I is in I0 and you also have is in I0. Right? Now this is equal to 1 to n summation j is in neighbor set of I. The probability, well, what is the definition? You want R transpose Vi is greater than equal to T for I to be in I0, and R transpose Vj is greater than equal to T if you want J is in I0. Now just to make things clear over here, what is random in this expression is the vector R that is chosen according to the standard Gaussian distribution. Okay. Now in the max cut example, we had chosen a random vector on the surface of the sphere. Here it's a standard Gaussian distribution, and because the standard deviation is 1, you can intuitively think of it as being close to the radius 1 ball. Okay. So what we are asking for here is, well, you're going to choose a Gaussian vector. This is a unit ball, so you have Vi, and notice that because ij is an edge, Vi and Vj are at an angle of 120 degrees or 2 pi by 3. Okay. Now the random vector R can lie anywhere in the space, okay, because it is a random Gaussian vector. It's distributed over the entire n-dimensional space, but you expect it to lie somewhere around the one-dimensional ball, okay, because the probability of it lying too far away is much smaller. So now, given this Vi and Vj, like we did for max cut, let us analyze the probability that the random vector R has got nice dot product with both Vi and Vj at the same time. Notice that these two events are not independent, because if it has large dot product with Vi, conceivably it will have small inner product with Vj. So let us try to mark out the possible regions where R can lie. Okay. So this is the figure we have. We have Vi and Vj at an angle of 2 pi by 3. Now what is the region where the inner product between Vi and a vector R is greater than equal to 2 pi by 3, is greater than equal to T. Okay. So now that should be the following. So along Vi you go up to T, because Vi is a unit vector. You look at this region. Okay, so this part is T, and this region over here has got inner product between Vi and R to be greater than equal to T. So if R, which is drawn randomly, lies anywhere in the shaded region, you'll have the inner product with Vi being greater than equal to T. Similarly, with Vj, if you take a distance T and draw a perpendicular line, then the corresponding dot product in this region has got Vj comma R inner product is greater than equal to T. So maybe I should not introduce this particular notation, R transpose Vj. This is Vi times R is greater than equal to the threshold T. Of course, the threshold T, I've drawn it in an exaggerated way to make things clear. The T that we choose will be actually much closer. Okay. So this region is where both of these are satisfied, right? The shaded region, which is the intersection, and that exactly corresponds to the event that we have. Now, if Vi transpose R is greater than equal to T and Vj transpose R is greater than equal to T, this geometric picture gives us where the shaded region lies. So the shaded region, I claim with a little simple geometry, is the following. This should be 60 degrees, right, or pi by 3. Therefore, the distance from the center of the circle to the intersection of these wedges is exactly 2t, right? So the wedge space actually is a subset of this particular half space H, which is at distance 2t from the origin. So I'm going to upper bound this event by the probability that R lies in the half space at distance or lies beyond the half space at distance 2t from the origin. Okay, and that is nothing but the probability that the norm of R is greater than or equal to 2t. So the whole expression above, I'm going to upper bound by, well, the two summations I keep to be the same, to t, right? And actually you can view this as just the projection of R in the plane form by the Vi and Vj. That is still a standard Gaussian distribution, right? And we can use that property. You can as well view it in the original space because the half space as defined lies in the original space, so it doesn't really matter. The bound still holds. Now what does this give us? This quantity is n of 2t. Okay, because recall what is the probability now that norm R is greater than or equal to 2t. It's just n of 2t by definition. So this expression is of maximum degree delta, so every I can have at most capital delta neighbors. So this is less than or equal to n times delta n of 2t. So now if you go back to our expression over here, we have bounded the first term by n times n of t, and this we have eventually bounded by n times delta times n of 2t. So this implies that the expected size of the independent set that we output is at least n times n of t minus n times delta n of 2t. Again, delta is the maximum degree in the graph. I've just pulled the n out. So this is our factor gamma, which is the expected size of the independent set. Okay, because we wanted an independent set of size at least gamma times n. Now, how do we estimate this quantity or prove a lower bound on it? We use the bounds on n of t that we had defined earlier. The gamma that we get is greater than or equal to, well, n of t, if you recall, is at least 1 over t minus 1 over t cubed times 1 over square root 2 pi x minus 2 minus delta times, again the upper bound was just 1 over t, but now t is replaced by 2t, so this is 1 over t times 2t times there's again a square root 2 pi here, exponential minus 4t squared by 2, right? So using these two quantities, we can actually now set an appropriate value of t that balances out the first and the second term. So we set t to be equal to square root ln delta square root 2 over 3. Okay. And we'll assume that the maximum degree is at least something in the graph, because otherwise we could stop the coloring before that. It's at least some constant, say 2 or something. Or delta is greater than equal to 8 or something similar. Else we could just stop the coloring at that point and color the remaining graph with a constant number of colors. So this gives us that exponential of minus t squared by 2 looks like exponential in minus ln delta times 2 over 6, which is exponential minus ln delta over 3, which is delta raised to 1 over 3. Minus 1 over 3. Okay, so substituting this back, we get gamma is greater than equal to, well, I'm going to ignore the 1 over t cube term, the first one. I'm just going to keep the 1 over t term. Delta, you have a constant 1 over square root 2 pi hanging out. The first term, which is exponential minus t square over 2, is just delta raised to minus 1/3 minus delta times 1 over 2t times delta raised to minus 4/3, because it's exponential minus t square over 2 raised to 4. This gamma is at least, well, I'm going to just ignore the constant terms, and you get half delta raised to minus 1 over 3. Okay, there's no 2t here, just a 2 here. I've pulled the t out. So some notes here. I've ignored the 1 over t cube term by setting t's greater than equal to 2. So at most a 1/8 fraction of this minus something smaller. So this is at least omega delta raised to minus 1 over 3 by square root ln delta, which is what we had promised to start off with. So that kind of finishes the proof of what we want. That is, what you have shown is that the expected size of the independent set that is output by the algorithm is at least this gamma fraction of the number of vertices. Okay, so you pick out an independent set, color it, repeat the process on the remaining graph, which has at most 1 minus gamma times n vertices, until you have at most one vertex left. Now, what is an upper bound on delta? Notice that I've only given you guarantees in terms of delta. Okay, and this, by the way, just to finish up, gives us a delta raised to 1 over 3 square root ln delta times log n coloring. This is what I argued before we started this analysis. Now, just graphs can have degree up to n, right, and still be tree colorable, up to omega n and still be tree colorable. So what is the bound that we can use on delta to express it in terms of n? So it turns out setting delta less than equal to n is not good enough. Because all that you get is a very bad approximation ratio. Well, I take that back. It's not really bad, because we get only a order n raised to 1 over 3, which is n raised to 0.33 coloring. But we would like to do slightly better, as we expected a n raised to 0.25 coloring. And the trick to do that is combine this with the Wigderson's trick that you had seen before. Okay, that is, you remove the high degree vertex in the graph over some threshold delta and color that and its neighbors using 3 colors. Repeat until you have only low degree vertices in the graph. Okay, and on the low degree vertices, you actually use this algorithm, which gives a good guarantee, right? So at what point do you stop and call it low degree? Well, that's the trade-off that we need to fix. The first step, or the number of iterations of that algorithm, if you recall, with threshold delta is approximately n divided by delta. Okay, and so you use n over delta colors because you use 3 times the number of iterations colors. And you want the second part is you're going to use delta raised to 1 over 3. And so to balance this out, we want Tn over delta is delta raised to 1 over 3, which gives us delta is equal to n raised to 3 over 4. Okay, and now substituting this back, our coloring therefore, which is balanced in the first and second parts, overall is just n over delta, which is also equal to delta raised to 1 over 3. I'm ignoring kind of the lower order terms. And if you calculate this, this comes out to n raised to 1 over times log n. Okay, so asymptotically, you're going to use n raised to 0.5 times log n colors to color the 3 colorable graph that is given to you. So that was the entire algorithm for this problem. It's quite an interesting algorithm that starts off with a relaxation that's not just coming from 0, 1 vector, 0, 1 variables or quadratic forms. Rather, it uses the vector structure quite explicitly, and then using the geometry and some properties of the Gaussian distribution, you could get it down to this. So that's all for today. Next time, we'll move on to a slightly different topic, which is the use of metric spaces in the design of approximation algorithms. Thank you.